Welcome. I'm Christopher DiLeonardo. You're a professor for Introductory Geology. I want you to think of me less as a teacher and more of a guide on a journey of discovery. Discovery of a planet that you've lived on since birth, but may be alien to you.
Your discovery of the Earth begins here, a world on which you were born, but in many ways remain a stranger. Your daily stroll through the familiar environs of your college campus, neighborhood, countryside, or coastline belies the hidden world all around you, from the microscopic scale of the crystalline structures within the rocks and soil you walk on, to the architecture of the crust and planet beneath your feet. There is a universe of which you are only partially aware.
There are great forces at work shaping this universe and the landscape around you. Forces driven by the Earth's own internal heat engine and the relentless power of superficial processes driven by the sun. You are embarking on a journey of discovery of an at once familiar and at the same time alien world you call Earth. Your tools of discovery are what you carry with you, not the ones you think of when we commonly think of somebody doing exploration. It isn't about the boots, hats, compasses, rock hammers, or other equipment that might be carried with an explorer into the field, but rather the critical thinking skills and knowledge of the science of the earth that you carry in your head. Those are the skills that will be developed by engaging in geology, the study of our home world and other similar planetary bodies. Commonly, when asked what geology is, people simply think of it as the study of the earth. And that's somewhat correct, but doesn't quite get to the nuances of the meaning itself or what geology is. I'm sure you had some idea what geology was. You wouldn't have signed up for the course. But let's explore the meaning even deeper. When people say that geology is the study of the earth, they're taking that from its derivation, how it formed. It's from the Greek gaia, meaning earth, logos, to study. So yes, it is the study of the earth, but how often in the English language does the derivation of a word equate to its actual meaning? I'll give you an example. Later in this term, when we're studying volcanism, we are going to encounter a word pyroclastic. Pyroclastic comes from the Greek pyro, meaning fire, and clastic, meaning broken. I assure you, this cloud forming over Pinatubo from the eruption in the 1990s in the Philippines is not made up of broken pieces of fire. It is rather made up of fragments of ash and dust and volcanic rock. That's what pyroclastic means. So in the same way, when we talk about geology, the meaning is much more than its derivation. In fact, geology is a scientific study of the nature, origin, and evolution of the Earth and other terrestrial bodies. This is a definition that you should become very familiar with. In fact, there are a lot of terms in the course, and the only definition of a term I kind of insist you memorize is this one, the meaning of geology. So that when you get through my course, if you remember nothing else, you'll remember what it was you were supposed to be studying from the beginning of the term. But the meaning also reflects the discipline of geology itself. In a general sense, we can separate geology into physical geology and historical geology. Physical geology deals with the composition, structure, processes of the earth, whereas historical geology deals with the changes in the earth over time and its origin. And if we look at this definition, when we talk about nature, we are referring to the composition, the structure, and the processes. In fact, the term nature is a very good one because we apply it in everyday language as well. When we talk about the nature of a friend, we might use that nature as a predictive tool. Well, it's in his nature to help people on the streets. So you can actually predict when he sees someone who needs help on the streets that he's going to jump in and engage that person. In the same way, we want to be able to be predictive about the Earth by understanding its nature. The origin of the Earth is something we're only going to touch on briefly in this course because this course in Introductory Geology deals mostly with physical geology. So we study the nature of the Earth. We'll talk briefly about the origin of the Earth. You'll see it in your readings. But this idea of the evolution of the Earth, the term evolution simply means change over time. And we are not so concerned in this class with what changes have occurred on the Earth, although we'll get some insight into that. We are very focused on how change occurs on the Earth. And in this way, we really understand that a lot of this course is about Earth processes. It's about the processes that act to change the Earth. In terms of other terrestrial bodies, and I'm asked about this quite a bit because students walk up and tell me, what does that mean? Other terrestrial bodies refer to other Earth-like bodies that you might encounter. Now, this would be any of the terrestrial bodies of the inner solar system, the Earth-like bodies. For example, Mars would be the moons that we find both in the inner and the outer solar system. It would also refer to asteroids. It would refer to meteorites, fragments, and fragmentary particles that have come from outside our planet onto the Earth. Geologists study all of that. And to think about that, you think about a place like Mars. If you wanted to study volcanism on Mars, it wouldn't be an astronomer who studies that. An astronomer studies everything from orbital mechanics on the one hand to anything that we can see in terms of light coming in from an extraterrestrial source. But to study volcanism on Mars, you would want someone who has studied volcanism, and that would be a volcanologist. So we have volcanologists who literally study both the Earth and volcanism on Mars and other terrestrial planets. And that's something that you can kind of understand. It's about the training. We can see this in all kinds of processes, like people who study sand dunes on Mars, people who study the composition on Mars. So I want you to just broaden that a little bit to understand that geology studies not only the Earth, but other terrestrial bodies. Now, the other aspect of this that's really important is that first part. It's not any study. It's specifically a scientific study. And we're going to look at that. But first, let's take a look at what it is that geologists and other geoscientists study. The work of geologists is as varied as the subdisciplines out of which they come. Some study crustal structures, while other geologists study types of rocks and the processes by which they form. Still, others consider the environment, study water quality, study the interactions with humans. Others study the dynamic processes that act to shape the Earth or reflect the Earth's internal heat engine. Many others apply physics or chemistry to the study of the Earth as an integrated system. You can find geologists out in the field studying the climate changes that have occurred over time on Earth. But you can also find them studying clues to ancient life, studying the interactions of geology with the biosphere and the changes that are occurring in the Earth over time. Others work for industry, while some geologists study the ocean floor. Others study the Earth from space. And we can find geologists, even in the far reaches of our solar system, studying the composition and structure and processes of other worlds. Though the subdisciplines of geology seem varied, and the type of work geologists are engaged in numerous, they all share a common scientific approach to solving disparate questions about the Earth.
What do you think of when you hear the word science? It actually has a number of meanings in English, which can be very confusing to someone who uses it in everyday speech. More often than not, when somebody uses the term science, they're referring to something like political science, military science, library science, referring to science as an organized body of knowledge. Now, that may be true, but when a scientist uses the term science, they mean something altogether different. To the scientist, she or he uses the term science to refer to a very specific approach to solving problems or answering questions about the natural universe. It is about the approach. It's about a way of thinking. Now, I know what you're saying. Thinking is, well, thinking, isn't it? But not all thinking is created equal. In the broadest sense, you can either think by imitation or you can think independently. Thinking independently, as the term suggests, are thoughts that you self-generate, or the building of thoughts on top of something you have received from someone else. On the other hand, thinking by imitation, well, that's really about accepting as true something you have received from someone else, something you have been told, something you have read, something you saw on the internet. And even with that, it's a little more complicated because very commonly, if we're talking about thinking by imitation, it's not as passive as you might suppose. There's someone on the other side giving you the information and trying to get you to accept it as true. Commonly, you will see that when the information is being presented, little breadcrumbs of truths are put into that. Seemingly reasonable assertions are put in to lead you to a conclusion that what you are hearing you should accept as true. On top of that, the most important act in thinking by imitation, which is a very, very active thought, is to accept it. And that's based on faith. It requires faith that what you were receiving as information is true or correct, even though you don't know it to be true or correct. Now, I also know what you're saying. You're sophisticated. You're a person of the world. You live in the Silicon Valley. You're a skeptic. You don't have faith in anything. Well, I want to test that proposition at the moment and ask you a question. Have you ever been to Australia? And if the answer is no, how do you know it's there? It could be the world's greatest conspiracy, started by the British in the late 1700s. They had too many prisoners. They put them on boats, sent them to the southern oceans. When the boats came back empty, people asked questions. Where are all the prisoners? They had to come up with some answer. They said they left him in Australia. Yeah, that's it. We left him in Australia. Perhaps there is no Australia. Perhaps the Sydney Olympics was a cleverly devised ruse and they flew people into South Africa at night. Nobody knew. Outback Steakhouse, part of this carefully considered ruse. And well, Paul Hogan, Welshman with a bad accent. There is no Australia. You just don't know. I, too, accept that there's an Australia. I mean, it would be absurd to think otherwise. But it brings about a point. There are a lot of things that we don't know firsthand that we accept as true. And in science and in independent thought, you have to put that aside And when you receive information, you have to be thoughtful about what it is you're receiving. But in terms of independent thinking, there are two different approaches to it. And the one that permeates most everyday thought, that is the greatest part of scholarly thought, and even is used in our courtrooms around the world, is something called argumentative reasoning. In argumentative reasoning, you put forward a proposition, and then you find all of the evidence that supports that proposition. It could be a thesis about the causes of the Civil War, and you find all the evidence to support your thesis. It could be that you have others who are doing scholarly work who have a different idea, and they put forward their thesis and put all the evidence that supports it. Now, there's not anything wrong with this approach, but it isn't what we mean by science. And one of the great problems over the years is that people confuse argumentative reasoning with what happens in scientific methodology.
To you in the classroom?
Well, he said at first the Earth was too hot for any life. And then it cooled down a mite, and cells and things begun to live.
Cells?
Little bugs, like, in the water. And after that, the little bugs got to be bigger bugs, and they sprouted legs and crawled up on the land.
And how long did this take, according to Mr. Cates?
A couple million years, maybe longer.
Right there, gentlemen.
Then come the fishes and the reptiles and the mammals. Man's a mammal.
Along with the dogs and the cattle in the fields. Did he say that?
Yes, sir.
Now, Howard, how did man come out of this slimy mess of bugs and serpents, according to your professor?
Man was sort of evoluted from the old world monkeys.
Did you hear that, my friends? Old world monkeys. According to Mr. Cates, you and I are not even descended from good American monkeys.
Science isn't about argumentative reasoning. It doesn't take place in a court of law. It's not a debate. Science is a particular methodology. It truly is an approach, a unique one, to solving problems and answering questions about the natural universe. I'm sure since about 7th grade science class, at least, you've heard the term scientific method. And I don't like using the term, mostly because I've spent too many times volunteering for middle schools around the area, being a judge, where you come up to a student who has some elaborate experiment that they've done or project that they've constructed, usually with a lot of parental help. But they have a 3x5 card that they've told they need to check off, and it had 5 steps of the scientific method. In fact, when I see this in books or hear it talked about, there's always 5 steps. But if I were to get my colleagues on campus, say the other earth scientists and the people next door in physics, or go over to the science center on campus and pick up the chemists and the biologists, or go across campus to the south gate and find my friends and colleagues in environmental science, we may have 18 scientists gathered. We would have 27 different versions of the scientific method, apparently all with 5 steps. In some versions I've seen in middle school, step 1 is get question. This is kind of like asking, what are the steps for preparing your wedding? Step 1, find groom. You kind of assume you already have a groom. You kind of assume you already have a question. It's not about the number of steps. In fact, what bothers me most about the 3x5 cards that I see these young students with is this false idea that science is about a single person somewhere in a room with brown fluid boiling on a Bunsen burner, and them wearing a white lab coat, and then checking off 5 steps. This isn't what happens when campus opens up. And if you were to come see me in my lab on campus, if there's brown fluid boiling in the lab, turn it off. It's coffee. It shouldn't boil. It isn't that. We get this considerably wrong idea about science. Science is a very communal effort. A scientist engages in a process, but that process may not begin and end with them. That process may incorporate all kinds of other scientists who are feeding in on this single question and idea and thought. So I like to gather all of this into what I call the scientific methodology. It really takes all those steps of scientific methods and folds them into one place. Let's look at that. So you have a question, and it starts with observations about that question. This is not different than other scholarly pursuits, by the way. What makes science different and unique is how the flow works, where it is going, and we'll get to that in a moment. By the way, numeric measurements, numeric observations are referred to as data. When we use the term data, it's not just numbers, it is numeric observations. So if you take a temperature, that would be data. If you look at the radiance of a body, that would be data. If you look at a particular type of rock and assess how it looks, that would be an observation, but it would not be, quote, data. Now, what you do with these observations is really important. You go through a process called analysis, and feeding into this analysis is something called literature review. Literally, you look at what has been done previously in the science that applies to your particular question. By the way, I'm showing this here as if it's some sort of linear process. Not only is science not a single person doing it, it's not quite as linear as presented here. Commonly, when you have a question, you would start a literature review right away to see what other people have contributed on that particular question or problem about the natural universe. Analysis here is simply looking at the observations you have, folding in the literature review, and looking at what is absolutely important or key to what you're doing. Let's take a completely different question for a moment and see how this approach would work. So let's say after watching this lecture and wondering, am I going to stay in this crazy guy's class for the rest of the term? You get in your car and you drive to a local Starbucks. On your way to the Starbucks, you're thinking about the class, you're thinking about your term, you're thinking about your investments, and the light suddenly changes. And you apply your brakes, and everybody around you applies your brakes, and you hear a terrible metallic squealing sound. Now, you could think about that terrible metallic squealing sound and ask yourself, what's causing that? Well, think about the observations. There's a blue sky. I'm going to get Starbucks. I'm on the corner and the Starbucks across the street and I can already smell the coffee. I'm thinking about my salted, malted Frappuccino. I had to come to a sudden stop. The light turned red. I applied my brakes. People around me came to a sudden stop. They applied my brakes. There's all kinds of observations here. Not all of them are relevant to your question, and analysis is about sorting through those observations, along with the help of literature review. I mean, you might go online trying to answer this question and think through what causes metallic squealing sounds when applying brakes. And from that analysis, you come up with ideas, educated guesses. We refer to this in science as hypotheses. Hypotheses is the plural of hypothesis, an educated guess. And you would come up maybe with several. One hypothesis might be, it's my brakes. They're wearing. An alternate hypothesis might be it's somebody else's brakes that are wearing. From that, two different things can happen that are still part of scientific methodology. Either you could pick a particular hypothesis and go after that. That's referred to as working hypothesis. And classically, that's kind of the way science worked for many, many decades. Probably a better approach is what is referred to as multiple working hypotheses. In multiple working hypotheses, instead of adopting one, you adopt multiple, the likely hypotheses. And there's a real good reason for doing this, because whether you're doing working hypothesis or multiple working hypotheses, science is about what happens next. What happens next is you test your hypotheses by prediction. So in the case of your car and the squealing metallic noise, you have several hypotheses. One could be it's my brakes are bad. Two, it could be somebody else's brakes are bad. And a third hypothesis could be the Martians are coming down to take over the Starbucks. Turnabout is fair play, after all. And that's the sound that the Martian death ray makes on their spacecraft when it's warming up. I mean, not all hypotheses are created equal. Let's take a look at the two more likely hypotheses, though, right? So we'll look at and compare the hypothesis that it's my brakes versus somebody else's brakes. Under working hypothesis, you'd only take one hypothesis. So in this case, it's my brakes. And you would develop a test by prediction. By the way, the technical term for a test by prediction is experiment. That's what an experiment is. It's simply a test by prediction. And your test by prediction could be at the next light, I'm going to slam on my brakes and see if they squeal. So you go down to the next light, along with all these other cars that were with you, and you slam on your brakes, and yes, there's a terrible squealing sound. Of course, other people have slammed on their brakes. Have you resolved the issue? Not really. Did your hypothesis test by prediction? Yes, it tested out fine by prediction, because the prediction is if it's my brakes, when I go down to the next light and apply brakes, I'll hear that terrible metallic squealing sound. But you haven't really ruled out the other hypothesis. And this is really shining a light on the idea of multiple working hypotheses. Under multiple working hypotheses, you would adopt both of those. You would have to develop a test that is exclusionary, and that's how test by prediction works in the sciences. You are trying to disprove the hypothesis that you generated. So you come up with a test that if it doesn't pass, you know it's not correct. And if it passes, you have more confidence in it. You're not guaranteed that it's correct, but you develop more confidence. In multiple working hypotheses, that helps you construct an experiment that would exclude one or the other. So the experiment here could be, instead of going down the street and applying your brakes, you decide to make a left-hand turn, go into the Starbucks. After all, you wanted that salted malted frappuccino anyway. And you get into an empty parking lot and you look around, you don't see any other cars. Then you speed up a little bit and apply your brakes. Test by prediction. If it is your brakes, then you expect to hear that metallic squealing sound. If it was somebody else's brakes and they're long gone, you would expect to apply your brakes and not hear it. And if you don't hear it, that gives you confidence that it was probably somebody else's brakes, and it has eliminated the hypothesis that it is your brakes. And that is how science works. Science is about trying to disprove a hypothesis or hypotheses that you've generated. The more you try to disprove it and you come up with tests by prediction and it passes, the more confidence that you have in that particular hypothesis. Now, of course, that doesn't mean if you apply your brakes in the Starbucks parking lot and you hear that terrible metallic squealing sound that it really was your brakes. I mean, it could still be the Martian death ray warming up. There are no guarantees of a right answer in science. What you develop in science is an increasingly greater confidence in the hypothesis or model or theory that you have generated. And you're able to take hypotheses and ideas and conclusions that were not viable and eliminate them by test by prediction. This is what science is truly about. It does not guarantee you a right answer, but it does guarantee you reproducible results. In other words, if somebody else applied the same experiment under the same conditions, they would be expected to get the same results. Now, what do we do once we've come up with a hypothesis and we've tested it? Well, this is important to note. At that point, you're going to pass it on to the rest of the scientific community. And something I really need to emphasize about this structure, you're doing science if you're anywhere in the process. You don't have to go all the way from observations or test by prediction. You don't have to necessarily do the experiment yourself to be engaged in science. As long as you're engaged in process that's moving down to that test by prediction, that experiment, you may make observations and do analysis and publish on that. You may develop hypotheses and put them out. Somebody else may pick that up and run with it and develop a test by prediction, an experiment. Or you may propose an experiment and somebody else does that. Probably one of the most famous experiments in history is a test of Einstein's theory of relativity with regard to gravity and light. Einstein said that gravity isn't, as Newtonian mechanics suggests, simply a force between two massive objects in the universe. Einstein said that gravity actually is the bending of time and space itself, and that things that have no mass at all, if traveling through time and space, will be bent around these warpings of time and space by gravity. Light, having no mass, would be one thing you could use to test it. And so here was the experiment. The experiment is, during a total eclipse of the sun, light passing very close to where the sun is in the form of starlight would be pulled closer to the sun than where those stars should appear with respect to other stars in the night sky. Einstein was able to use his calculations of how time and space would bend to predict exactly how much shifted that star light and pinpoints of light would be towards the now darkened disk of the sun during the eclipse. He did not do the experiment himself. Astronomers did observations in parts of the world where they could see that total eclipse, and it turned out that Einstein's theory of relativity passed that test by prediction like gangbusters. But my point here is, no one would ever accuse Einstein of not doing science because he didn't get from step 1 to step 5 on his 3x5 card. It is a very organic process, and it is a very communal process. Somebody publishes data, analysis, hypothesis, and somebody else might publish different hypotheses based on somebody else's analysis. Somebody may develop a new test by prediction. It is very, very communal. And this communal nature of science is very important. The other thing that's important about science is it needs to be disseminated for that communal nature to work. One place that this dissemination occurs is at scientific meetings, where scientists gather to share the results of their research with other scientists, either through poster sessions or more formal presentations. Beyond scientific meetings, the gold standard for disseminating information to other scientists is something called the peer-reviewed paper. These papers appear in scientific journals all over the planet and in the various disciplines. In the geosciences, there are many. I'm showing you two. One is from the Geological Society of America's Bulletin, and the other is Geology. In these and any other scientific journal, a process of peer review is part of the formal dissemination of ideas, thoughts in the sciences. These include taking your work and distilling it into a paper, similar to a term paper you might write. Now, you don't just do that alone. Normally, if you have co-authors, other scientists who've worked with you on the project, you would hand copies of your draft to them, And they, like good professors would, take their red pen out and are marking up the margins, asking questions, making corrections. And you would fold that into your paper. You might also go to colleagues and friends who have similar backgrounds and expertise or doing similar research to what you were doing and ask them to review the paper as well. Once you've done all of that, you put your final copy together along with a cover letter to the editor of the journal you are applying this paper to, and telling them why in that particular cover letter this paper should be printed in their journal. Now, the editor will read the cover letter and then will peruse the paper. The editor is a scientist, but doesn't necessarily have your expertise or background in this area of research. If they're convinced that there's a possibility this paper might be important to their readership, they will pass it on to someone who is an associate editor. The associate editor is another scientist who is doing part of their work as an editor for this particular journal, but they have expertise and research that is similar to your background, so that they know what you're writing about, understand the research. They read that in the cover letter. If they feel that the paper has some merit to be published in their particular journal, then they will reach out to 3 to 5 scientists around the planet who have exactly your kind of education and experience and expertise, who are also doing research in the very area you're doing research, and in many cases are people who have alternative ideas and thoughts to the ones you're presenting in the paper. You have to get it past that group of scientists. And what they do, again, like good professors would, they take out their red ink pen and they're marking up the margins, they are making corrections, they are asking questions. Those 3 to 5 copies, along with any notes and edits from the associate editor, land on your desk. And you do a rewrite. And you must address every question they've asked. If they've asked you to make a correction, you either make the correction or explain to the satisfaction of the associate editor why it is you shouldn't make that correction. You have to get it past that group before it actually gets published. And that is the gold standard for dissemination. It's how we gain a better understanding in the sciences and how we have greater and greater confidence to build on. In our particular study of planet Earth, we are literally going to be taking the work of scientists over the last couple hundred years who've been studying the Earth and apply it to our understanding, knowledge, and our discovery of planet Earth. So join me over the course of this term, looking first at dynamic processes, and then going on to see how those dynamic processes are recorded within the crust of the Earth.